Okay, welcome to Intro to Photonics. Last week we had been looking at ways of manipulating light, and with respect to that we started with how does light propagate through a medium, and then went on to look at using light polarization, manipulating light polarization. Can we let us say for example change the intensity of light, and so that is what we were looking at last week, and we said we can change the intensity, we can actually change the polarization of light using a anisotropic medium. And while talking about those, we came up with this specific thing about quarter wave plates and half wave plates, and I made a mistake here which was pointed out by the TA at the end of the last session. So, I said we are actually going to go through a rotation this way, but what will happen here is we talked about the incident polarization being like this into an on and half wave plate by theta, but while propagating that through the half wave plate, we said the EY component is getting flipped. So, the EY component will show up once it is flipped, that the actual polarization will show up here, and this is basically 2 theta. Okay. So, that is what we wanted to convey, but I did a mistake there in the last session. So, so far we have been looking at either extinguishing a polarization using a polarizer, or rotating the polarization or changing the polarization state using a half wave plate or a quarter wave plate. There is actually one more important application that I want to touch upon before we move forward, and that application is what is called optical isolator. So, question is, when you send light from a source, let us say a laser, you send this light and it gets into some other components over here. Okay. But some of that light could actually get reflected by those components, okay. And that reflected light can potentially go into the source. So, now you have a cavity, a laser cavity, let us say, that is based on 2 mirrors, and light is going out of that cavity, it hits some component and then the reflection is coming back and it gets coupled into the laser again. So, this is like an external cavity that is getting developed. So, now the properties of the laser is not only dependent on this cavity, but also what is happening outside based on this reflection, and that can change a lot of things. That can change of course, the power that is emitted, that can fluctuate, but it can also mean that there is fluctuation in the wavelength at which light is emitted. Okay. So, this back reflection typically leads to power as well as spectral instability. of the laser. Okay. So, you need to essentially introduce a component, the output of your source, such that it allows light to get transmitted in one direction, okay, but it should not allow light to come back. So, whatever component here, it should block, whatever component coming back, it should block that. Okay. So, that essentially means that this component, which we will call as an isolator, will need to exhibit a non-reciprocal response. So, before we talk about non-reciprocal response, let us just understand what reciprocity means. Reciprocity means that you go from left to right, you have a certain response from this component, and that response should be the same if you go from right to left, the opposite direction. That is, you are flipping the input and output, right. When you are flipping the input and output, if the response is the same, then you say that component is reciprocal. Okay. But that is not what we want. We want light to go from left to right, but we should not have light going from right to left. Okay. So, we need a non-reciprocal response. So, how can you achieve a non-reciprocal response? One way of achieving that is through what is called the Faraday effect. Clearly, it is named after Michael Faraday, who has a lot of brilliant observations. This is one of those observations, wherein what he observed is that when you look at response of certain medium, we try to characterize the response of the medium based on your permittivity. That is what we are looking at in the last week's lectures. But it so happens that there is also a response in terms of changing the polarization of light in the existence of an external magnetic field. Okay. That response is given by J epsilon naught gamma B cross E, right, where B corresponds to the magnetic field, in this case represented by the magnetic flux density along the axis of the material. So, through this magneto-gyration coefficient, this gamma is called the magneto-gyration coefficient. You have a gyration of the light polarization. Okay. In other words, if you have light polarization, let us say linear and going through this material, that polarization will be rotated by an angle corresponding to theta, okay, and where theta is given by minus pi times gamma over lambda naught n naught B times L, where B corresponds to the magnitude of your magnetic flux density along the axis of this material, and L corresponds to the length of this material itself. Okay. So, in the presence, essentially what we are saying is, in the presence of an external magnetic field, your light polarization, which corresponds to the electric field of your wave, that polarization is going to get rotated. Okay. And how much it rotates depends on the strength of the magnetic field or the extent of the interaction, the interaction length. Okay. Now, this factor over here is denoted by what is called the Faraday constant. So, its theta is just given by V multiplied by B multiplied by L, where V corresponds to the Faraday constant. Okay. Yes. So, yeah, so what is the significance of this being imaginary thing? It's basically saying it's a phase shift involved. So, that corresponds to a e power j pi sort of factor. Yeah. So, this is, in this case we are assuming that the B is constant. So, you can assume, or you can actually this would be a good idea, right? If B is not constant, then you are talking about possibly modulating that polarization coming out of this material, right. So, by modulating B, you can achieve modulation of the polarization state. Okay. And it's also dependent on the sign of B, right. So, if the B is in the opposite direction, the rotation will be in the opposite direction. So, the question is, can this B correspond to another electromagnetic wave? Possibly. You can say that, I mean, this just says that B cross E. So, the other B can correspond to another electromagnetic wave. However, the rate at which this change happens, the response of the medium would tend to be much muted, right. So, we are not talking about the response time. It's highly unlikely that this will respond to another electromagnetic wave at optical frequencies. Right, that was your question, whether it can respond to that, and basically, sorry. So, we are not actually quantifying the response time corresponding to gamma, right. So, that actually is medium dependent. So, I do not know of existence of a material that responds as optical frequencies. That does not mean that there is none, but as far as I know, it does not. Sorry, I do not understand the question. So, the question is whether this can happen in vacuum, and the answer is no. This is actually based on interaction with a material, and that material having a magneto-gyration coefficient corresponding to gamma, and gamma is different for different material, right. Just the same way as your relative permittivity is different for different material, gamma is different for different material, and I suspect gamma is also dependent on frequency. Okay. But the point I want to make is that you could achieve this. Now, if this material, if this material was a black box, right, you could, when you say your polarization is getting rotated, what could be in that black box? What else can you imagine can give you a rotation of your polarization? Halfway plate, right? A halfway plate could do that rotation. But in a halfway plate, if you had done this rotation and you flip, which is the input and output, or rather you come back with this polarization as the input, okay, you come in with this polarization and angle theta as an input from the right side, it would have gone back to this linear polarization. In other words, the halfway plate would have been completely reciprocal in nature. Okay. But this Faraday effect is not reciprocal. Why? Because the sign depends on which way the rotation happens, depends on B cross E. In one case, B is oriented along the direction of propagation, in the other case the B is oriented against the direction of propagation. So, the rotation would have been in the other direction than what was happening in this case. So, in this case, for Faraday effect, in this magneto-gyration effect, you would have gone out, if you came in with that polarization, you would have gone out with 2 theta as your polarization of the light that is going in this towards the left direction. Okay. So, this is actually because of the non-reciprocal nature of this Faraday effect, right? Yes, that is a question.
If we put this tube after that theta angle and with beta direction, what will be the output there? Theta.
Sorry, if we put
This tube now, we put it after this theta and we put it after that theta.
right.
So, and beta is in that direction, B is in
That direction, yes.
What will be the output?
So, the question is, if we had another rod like this after this output, after it is rotated by theta, it would have gone 2 theta again.
It's going to 2 theta only if you do it over here.
So, that is right. So, it is going to 2 theta. In this case, we are looking at it from a perspective of building an isolator, right. So, the question is, can we use this? We are not talking about just getting rotation. If you want to get just rotation, theta, 2 theta, whatever, you would have just used a halfway plate and achieved that rotation.
You just said that the direction of theta will depend on the
Orientation of the magnetic field with respect to the electric field, yes.
If B is in this direction or this direction, we are getting.
So, if I had another crystal after this, and in that crystal, let us say the B is in the opposite direction and of the same magnitude, both the crystals are the same material and the same length, then it would have gone back to the original polarization. Exactly, but now we are talking about reflected light. So, reflected light going from right to left, right. That reflected light would have gone to 2 theta because of this non-reciprocal nature. If it was a reciprocal device, it would have gone back to the original polarization itself. So, how would you build an isolator based on this effect? That is simple, right. So, you can basically put a polarizer which allows only this polarization, right. So, that is how you got this output polarization like this. But that polarizer, if theta So, if this theta is 45 degrees, right. So, you have rotated your polarization by 45 degrees going from left to right, but coming back it would have rotated 90 degrees with respect to the original polarization, right. And then when that goes into the polarizer, what happens? That would have been absorbed, right. So, you would not have any light going in this direction. Okay. So, you had light going this way, go through that a material, go through theta equals to 45 degrees and go through any back reflection, right. But that back reflection while going back would have been rotated such that 2 theta is 90 degrees and then it is going across this polarizer, which would the polarizer would have blocked that orthogonal polarization. So, this entire device now consisting of a polarizer followed by this Faraday material or a material which has this gamma, the magnetogyration, that would have together worked like an isolator. So, the question is, yes, this would work only if theta is 45 degrees. Yes, to get maximum isolation, you need to have theta set at 45 degrees. And there is something very important about this. You go back and look at the Faraday constant. The Faraday constant is inversely proportional to lambda, the wavelength of the light that is going through. So, a Faraday isolator, that is what this device would be called. A Faraday isolator for one wavelength will not provide the same isolation as some other wavelength, because for some other wavelength theta would not be 45 degrees and you would have to go through Malus law essentially to determine how much light is actually going through, right. So, it won't work as perfect isolator. Now, this isolator typically provides you isolation of up to 25-30 dB, the typical numbers, meaning only 0.1% of the light that is going in the forward direction is going back into the going back in the reverse direction, right. That is good for most cases, but if you have a high power source, let us say a 100 watt source, 0.1% of it is still 100 milliwatts, right. So, 100 milliwatts may be a lot of power to handle at your original source. So, certain applications require you to have 50 or 60 dB isolation. So, what would you do? You can cascade two of these things, and of course, when you cascade it, you have to be careful that the polarization alignment is taken care of. The second polarizer is aligned at 45 degrees. It's a question there.
So this also assumes that the reflected wavelength, the component that is reflecting the wave is not changing the polarization.
Yeah, so the reflection, that is true. The assumption here is that the reflection is not changing the polarization state, right, which normally it does not. But yeah, if you have some anisotropic response on the other side, then this will not work. However, in those sort of conditions, I did not mean to talk about this very much, but since there is a question, I will just mention this. So, this is the principle for a what is called a polarization sensitive isolator. It is called polarization sensitive also because of the fact that only if you have polarized light you will have maximum throughput, right. Only you have polarized light matching the input polarizer, then you have maximum throughput. If you have circular polarization, for example, coming in, that polarizer right up front would have taken out one of the polarization components. So, half the power would be lost right at the polarizer, the front end itself, right. So, then that sort of thing would be lossy. So, what you would need in that case is a polarization insensitive isolator. I did not actually expect so many questions in this topic, and I am glad I am getting those many questions, because that means that you guys are really getting into this topic or showing interest in this topic. So, keep them coming. Okay. So, you could have a polarization insensitive isolator, which basically says, okay, I will split my polarization such that my vertical polarization goes that way, my horizontal polarization goes this way, and then I would have a mirror here and then go through this. Then I go through my Faraday rotation material, okay. And then I go through, so this is my FR material which is rotating this polarization by 45 degrees, and then I would go through a half wave plate, okay. The half wave plate would rotate the input polarization, it's set such that it's rotating the input polarization by a further 90 degrees. Why that is needed is because of this particular configuration that we have. So, you put another polarization splitter here. So, the polarization splitter, what it does is any horizontal polarization it reflects, any vertical polarization it transmits. So, both these polarizations will go together the side. So, here now my input can be any arbitrary polarization consisting of both my x and y components, right. That polarization will be preserved as it propagates through this structure, okay. And similarly, any arbitrary polarization coming back is going to go through this polarization, this what is called the polarization diversity configuration, because it separates out the two orthogonal polarization, the path for the two orthogonal polarization, but it effectively will end up blocking the wave just as we talked about. Okay. So, in this case you could have some other arbitrary polarization coming in as well, but you could find a way of extinguishing that, providing isolation for that. So, that is a polarization insensitive isolator. Okay. So, just to give you a clear picture here. So, this is 45 degrees, but after going through the halfway plate it would have been this horizontal polarization. So, vertical is becoming horizontal, and when you trace your way back, this horizontal would have gone back to 45, but after going through the Faraday rotation it would have been 90 degrees. At 90 degrees this polarization beam splitter will reflect, because the beam splitter is such that it is reflecting horizontal polarization. So, when coming back it would have been 90 degrees and that would have been reflected over there. Okay. So, it is not going back to the source. So, some of you may not be following this polarization insensitive scheme, and I can take questions on that separately, but it is okay if you do not follow that. If you understand this polarization sensitive isolator, that is all I wanted to convey to you today. That is right. So, it is actually, so look at it this way. Normally if it is a reciprocal device, it would have gone back to the original polarization, right, and in this case it is non-reciprocal, that means it is going in the opposite direction because of the orientation of the magnetic field with respect to the incoming polarization. The magnetic field is reverse, yes. Okay, do not go so much into the orientations yet, but just think about it as this way, right. So, in one case if it was reciprocal, it would have actually given you the original polarization itself, and in this case because the magnetic field is opposite, right, because my electric field or the incoming wave is in this direction, but the magnetic field is in this direction. Because of that it is going in the opposite direction. The polarization is in the, that is essentially the non-reciprocal effect. There is a very fine point over here. When we talk about a polarization insensitive isolator, we are talking about light not going back towards the source. So, we are blocking this light, but we are actually having light go into that other direction. So, there is an opportunity to pick up that light and use it also, or in other words, maybe your intention is to go from port 1 to port 2, but anything from port 2 you actually want to extract from port 3. Okay. Does that remind you of something that you have come across? That is the functionality of a circulator. So, a polarization insensitive isolator can actually be modified to provide you this circulator functionality as well. So you can extract light coming back from the other direction. Okay. So, you can do 1 to 2, but anything coming from 2 goes into 3. Okay. So, already out of time. I actually wanted to go into a different topic, but that is fine. We can meet on Wednesday, and then we will talk about. So, where we are going with this is, so far all this is still very much linear response from the material, but what we will deal with in the next lecture is what if the material responds in a nonlinear fashion. One key point there is, as long as you have a linear response, whatever your incoming frequency is, the same frequency will go out. Okay. For any linearly respond material, whatever is the excitation frequency, the output frequency will be the same. But when we go to nonlinear response, you have an opportunity of changing that frequency. So, the outgoing frequency may not be the same as the incoming frequency. Okay. So, that those aspects we will discuss in more detail in the next lecture.